I am Dr. D. Madhavi. Today my topic of discussion is sorting. Applications of sorting. So there are many applications of sorting. The first one is you can perform efficient searching. So in binary searching, what is the requirement? The requirement is all the elements are to be sorted in an order before searching. So binary search is more efficient than linear searching. Similarly, uniqueness testing. How unique, whether the data contains any duplicates or not, that can be identified. And deleting duplicates and prioritizing events. We are arranging the elements in an order. Similarly, in the same order, you can assign ranks to the data records and then access them according to their ranks. Similarly, frequency counting. If so many numbers are there in the data set that are repeating, so you can count how many times a particular number is occurring in the given data set. So for that also you can sort the numbers so that all the numbers of equal value will be at one place, and then you can just count using a counter. So frequency counting can be implemented using sorting. And for reconstructing the original order also, you can make use of sorting. Similarly, to perform set intersection and union, the numbers in the set will be sorted first, and then the union operation or intersection operation will be applied for getting better result and faster results. Similarly, the next one is finding a target pair xy such that x plus y is equal to some other number z. So here is the example for this. You just imagine this set containing these elements 1, 2, 4, 6, 7, 8, 10, 13, 14 and 17. You have to find a pair x comma y of numbers in this set such that x plus y is equal to some number 17. If your set is unsorted, you can check every possible pair. So which is very long process, and it requires order of n square complexity because you need to use two for loops, nested for loops. If your set is sorted, you can just start with the first and last numbers. The first number can be called as x and the last number can be called as y, and move through the set by increasing x and decreasing y. So if you take here x is 1 initially and y is 17, so it is too big. So you decrease y. So y is 14 now and it is 1 plus 14, 15. It is too small. So increase x. So next x value is 2 in the array. 2 plus 14. It is 16. It is too small. So again increase x. So x value is 4. 4 plus 14 is too big. It is 18. We require 17. So we go for the next one. That is, we are going to decrease y now. Y value is 13. So 13 plus 4, it is 17. So at this point, you can stop your loop and then you can return the output that you found a pair whose value is x plus y is equal to 17. So the simple solution is possible only if the elements of your array are arranged in a sorted order. So this particular method has order of n log n complexity for sorting and order of n complexity for finding the pair. So it will be, the time complexity will be in the form of linear time complexity. So this is one application, finding a target pair xy such that x plus y is equal to z. Now there are some more other applications like finding the closest pair. So given a set of n numbers, how do you find the pair of numbers that have the smallest difference between them? After the numbers are sorted, the closest pair of the numbers will lie next to each other somewhere in sorted order. Thus, a linear time scan through them completes the job for a total of order of n log n time, including the sorting. So finding the closest pair is one application of sorting. And the frequency distribution is another application. Given a set of n items, which element occurs the largest number of times in the set? Okay, for that also you can see, this is the frequency counting application we discussed earlier. And then selection, what is the kth largest element in the set? If the keys are placed in sorted order in an array, the kth largest can be found in constant time by simply looking at the kth position of the array. Similarly, there is another application called convex hulls. So, given n points in 2 dimensions, what is the polygon of smallest area that contains them all? So there are n points in 2-dimensional space, and we have to find out the smallest polygon that covers all the n points. So this is called the convex hull problem. The convex hull is like a rubber band stretched over the points in the plane and then released. It compresses to just cover the points. The convex hull gives a nice representation of the shape of the points and is the most important building block for more sophisticated geometric algorithms. But how can we use sorting to construct the convex hull? Once you have the points sorted by x coordinate, the points can be inserted from left to right into the hull. Since the rightmost point is always on the boundary, we know that it will be inserted into the hull. Adding this new rightmost point might cause others to be deleted. But we can quickly identify these points because they lie inside the polygon formed by adding the new point. So these points to delete will be neighbors of the previous point we inserted. So they will be easy to find. And the total time is linear after the sorting has been done. So in this class, we studied about the importance of sorting, the problem definition of sorting, and various types of sorting and how they are categorized, and then various applications of sorting. So thanks for your time, and we'll continue in the next